Well, it's been a privilege. Bruce Chapman introduced me to Father Spitzer, a year and a half, 2 years ago, and we got to talking about these topics, and he invited me to contribute an appendix to one of the chapters in his book, and I was grateful for that opportunity. And it's been a pleasure getting to know Father Spitzer over the last year and a half or so. So you've been introduced to the seemingly irrefutable fact that the universe has a beginning. And that doesn't matter whether you have classical Big Bang cosmology or you embrace an inflationary model. If you've got an average Hubble expansion that's greater than 0, the universe has a beginning. But that beginning was very special, and you saw some of that indicated in Father Spitzer's discussion of entropy. So, you might say we live in the Goldilocks universe. You know the story of Goldilocks and the three bears and the porridge that wasn't too hot and wasn't too cold, it was just right. Well, that's the kind of universe that we inhabit. And in particular, it's just right with respect to the initial conditions and just right with respect to the natural laws and constants. And let me just emphasize a little bit more about the initial conditions. What is an initial condition? Well, suppose I was going to throw a baseball to you. If I didn't give it enough oomph, it wouldn't reach you. And if I threw it too hard, it might hurt you. So if it's going to arrive and it's going to be a comfortable catch, I've got to impart just the right sort of impetus to it. So that would be an example of an initial condition. Now, our universe, you could talk about it as kind of beginning in an explosion. Now, an explosion you think of as kind of a messy event. And this is the point about entropy. The explosion in which our universe began was not a messy event. And if you talk about how messy it could have been, this is what the Penrose calculation is all about, essentially. It looks at the observed statistical entropy in our universe, the entropy per baryon, and he calculates that out, and he arrives at a certain figure. And then he calculates, using the Bekenstein-Hawking formula for black hole entropy, what the supermassive black hole, the singularity that would have constituted the beginning of the universe, what sort of entropy could have been associated with that. And so you've got the numerator, the observed entropy, and the denominator, how big it could have been. And that fraction turns out to be, as Father Spitzer said, 1 over 10 to the 10 to the 123rd power. Let me just emphasize how big that denominator is so that you can gain a real appreciation of how small that probability is. So there are 10 to the 80th baryons in the universe, protons and neutrons. Now suppose we put a 0 on every one of those, okay? How many zeros is that? That's 10 to the 80th zeros. This number has 10 to the 123rd zeros, okay? So you would need 100 million, trillion universes our size with a 0 on every proton and neutron in all of those universes just to write out this number. That's how fine-tuned the initial entropy of our universe is. And as Father Spitzer said, if there was a pre-Big Bang state and you have some bounces, that fine-tuning gets even finer as you go backward. If you can even imagine such a thing. So that's the fine-tuning of the initial conditions that we observe. There's another kind of fine-tuning that's characteristic of the natural laws and constants in our universe. If we didn't have the right laws, our universe wouldn't be stable. So for instance, if gravity were an inverse cube law instead of an inverse square law, the planetary orbits wouldn't be stable, everything would spiral in, and life wouldn't be possible. So you need the right laws. And, you know, laws could mathematically, just from an abstract point of view, have taken many forms, but they have a particular form, and it's that particular form that makes the universe possible. Secondly, what about constants? Well, Father Spitzer mentioned gravity. Okay. It is indeed very fine-tuned. If you look at the scale of the strengths of physical forces, it varies over 40 orders of magnitude. The weakest is the gravitational force. The strongest is the strong nuclear force in the nucleus of the atom, which is 40 orders of magnitude. That's 10 to the 40th times stronger than the gravitational force. Now, there's no intrinsic reason in physical theory why the constants have the values that they have. They're measured empirically to have that value. Newton's constant is empirically determined. So if you ask, well, how wide could it have varied? How much could it have varied? Well, the range of strengths of physical forces that we observe would be a reasonable range to consider. So consider what would be the case if gravity could have varied over that scale. And what we see then as a consequence is that gravity is fine-tuned to relative to the range of strengths of physical forces to about 1 part in 10 to the 40th. To illustrate that, suppose that, to be generous, that the universe is 30 billion light years across, the observable universe, and we stretch a tape measure across that, okay? That comes out to about 10 to the 28th inches. Now, peg Newton's constant on one of those inches, okay? It's here in the middle, and the tape measure stretches off into the distance either way across the width of the observable universe, all right? Now, what would be the consequence of moving that Newton's constant, say, 1 inch to the right or 1 inch to the left? Well, 10 to the 40th divided by 10 to the 28th is 10 to the 12th. So with respect to the width of the whole universe, moving it 1 inch this way would increase the force of gravity a trillion-fold or decrease it a trillion-fold. If you decrease it a trillion-fold, no structures of any consequence are going to form. And if you increase it a trillion-fold, even Weight Watchers isn't going to help you. There wouldn't be any you to weigh that much, in other words. So here's another example. The cosmological constant is fine-tuned to 1 part in 10 to the 120th power. And what the cosmological constant does is it governs the rate of the expansion of space itself. Now, for years it was thought to be 0, but it turns out that it has a very small positive value. This was discovered back in 1998, and it falls within this constraint. If it were any larger, space would be blowing apart so fast that, again, you wouldn't get any structures, and if it were any smaller, the universe would recollapse on itself. So that's fine-tuned to 1 in 10 to the 120th. Those are 2 examples of the constants of nature that are also fine-tuned. So how are you going to explain this away if you want to try to preclude the possibility of an intelligent, transcendent agent who injected this information into the universe in a highly specific way? Well, what you're going to do, incidentally, this is kind of the illustration of a universe creating machine. You got to set all the dials just right, or you don't get a universe that's compatible with life. Okay. How can you get multiple tries at different initial conditions for the universe? Well, inflationary cosmology is something that can give you that. What is inflationary cosmology? It's the idea that a split second after the Big Bang, the universe underwent a period of hyper-exponential expansion that then shut off, and then the expansion continued at the more sedate rate that we see today. Why was this initially proposed? Well, it was initially proposed to explain away certain features of the universe that are rather puzzling. The uniformity of the cosmic microwave background radiation, the fact that the observable universe is almost flat in terms of its geometry. It has some properties of uniformity that are unusual, and inflation was invoked to kind of smooth things out in an initial stage so that when things blew up to be larger, they'd still be smooth. That is the essential idea. So what you've got then is a picture of, say, our visible universe here is in a larger bubble that was a result of the original inflation. And then prior to that, maybe there was another inflationary period that preceded it. And so you get the universe is a series of nested bubbles, is the idea. And that process, called chaotic inflation, which was described by Andre Linde, if it existed, would then give you essentially an unlimited number of tries at different initial conditions is the basic idea. And as Father Spitzer pointed out, the Borguth-Vilenkin theorem applies to that. That can't extend eternally into the past. There had to be an initial bubble because the average Hubble expansion is greater than 0. And as a consequence, even a multiverse that's inflationary in this sense has a beginning. And if it has a beginning, it requires a transcendent cause. But does inflation solve the problem of initial condition fine-tuning? Well, no, not exactly. In fact, it makes it worse in at least a couple of ways. The first way in which it makes it worse, it was invoked to explain the uniformity of the cosmic microwave background radiation, which is uniform to 1 part in about 100,000. To 1 part in about 100,000. The temperature from every direction of the sky of the cosmic microwave background is about the same to 1 part in 100,000, which is unusual. It requires very uniform initial conditions. Another thing that I mentioned was the flatness, and that's fine-tuned to about 1 part in 10 to the 15th. What happens when you invoke inflation? Well, there are different models of how this happens, but the basic picture is that it kicks in shortly after the Big Bang and operates in the first, 10 to the minus 37 to 10 to the minus 35 seconds of the universe existence, in which it causes the initial space to expand by a factor of about 10 to the 60th and smooth everything out. Okay? That's the basic picture. But there's a huge amount of energy involved in that, and it has to shut off just right to get our universe. And so the shut-off energy of the inflaton field, as it's so called, has to be fine-tuned, depending on the model, to either as low as 1 part in 10 to the 53rd to as much as 1 part in, again, 10 to the 123rd. So essentially, you've filled a smaller hole by digging a much deeper one, is the basic picture. The other problem is kind of related to the idea of the fine-tuning. Well, it is related to the idea of the fine-tuning of the entropy, but parallel to the idea of, well, what if the universe were bouncing? Well, in this case, it's what if there was an inflationary period at the beginning of the universe? So you've got essentially a situation in which you've piggybacked one explosion on the back of the other. And the end of the first explosion, or at the end of the period of inflation, you've got initial conditions that are fine-tuned to 1 part in 10 to the 10 to the 123rd. So the fine-tuning of the inflation itself, which is an entropy-increasing process, because it essentially is explaining things on the basis of thermalization, contributes exponentially to that, to the fine-tuning at the beginning. So you've got a hyper-exponential figure that's the end of a process that had to be also exponentially fine-tuned in order to end at that point. You see what I'm saying?
Yep.
So you've got an explosion that gives rise to another fine-tuned explosion. So the first explosion had to be hyper-exponentially fine-tuned. It makes the problem worse. So this is a problem for inflationary cosmology as an explanation of the fine-tuning of initial conditions. How are we going to go? But that doesn't do anything to explain the change, the laws and constants. How are we going to get the probabilistic resources to explain how the laws and constants of nature could be the way that they are and fine-tuned for life? Well, a resource for that was found in string theory. So what's string theory? Well, basically, string theory postulates that instead of particles, the fundamental constituents of nature are little filaments on the order of the Planck scale, which is about 10 to the minus 33rd centimeters in length, that can either be open or closed into loops, and they vibrate in different ways. And the way that they vibrate gives us the different particles that we observe. That's the basic picture of string theory. So what does that have to do with fine-tuning? Well, in order for string theory to work, it requires that space-time be 10-dimensional. 9 dimensions of space, 1 dimension of time. We only see 3 dimensions of space, right? So what happened to the other 6? Well, they're all curled up into little structures called orbifolds. And this is also on the Planck scale. But there are countless ways of what physicists would call compactifying those extra dimensions into those little curled up shapes. And the shape that those extra dimensions are curled up into influences the way that the laws operate in the macroscopic 3 dimensions. And the size of the different components of the compactification influences the strength of the coupling constants, the strength of the constants of nature. So here's a mechanism then whereby, okay, you've got all of these solutions of string theory. You can get different laws from different shapes of compactification. You can get different constants out of the sizes of the compactified features. So if all of these things could somehow come into existence, you'd have a way of varying the laws and constants of possible universes within the background laws of string theory in order to get a multiverse that had different components that, or different universes that had different laws and different constants. And if you had enough of those, maybe you could explain away the fine-tuning anthropically, because we wouldn't exist in those corners of the multiverse where the laws and the constants weren't compatible with our existence. That's the basic idea. It's called the string landscape hypothesis. Well, how are you going to get that to work? You need to somehow merge inflationary cosmology to take care of initial conditions and the string landscape hypothesis to get the different laws and constants. So the idea then is that you have these different compactifications, and they can transform from one to the other through the quantum decay of one of the features of the compactification that will lead to another universe of lower energy. So you start off somehow way up in the string landscape of energy, and then you cascade downward through the different compactifications of lower energy. And somewhere along the way, hopefully you get a universe that has the properties that ours has. Well, the assumption that you have to start in a really high state is a postulation, the only justification for it being that you need it in order to make the model work and do what you want it to do. Furthermore, think about the structure itself. I say bread-making machines, anyone. You're making a bunch of loaves of bread, right? And it's the product of a bread-making machine that's been programmed to do that. Well, here we've got a whole bunch of different universes that are being churned out of the mechanism of string theory. This mechanism is being invoked to explain the mechanical character by which universes can be generated, and you get one that looks designed over here. But what about the bread-making machine itself? It has laws that govern its behavior. Otherwise, it wouldn't work, and it wouldn't produce loaves of bread. Or in this case, it wouldn't produce universes. So really, all you've done is push the design problem up to the next level, and you can ask about the design of the bread-making machine itself, or in this case, the universe generator that's constituted by string theory or M theory and the landscape. What else? Well, there's another problem with the landscape in that it seems to suggest that we should observe low-energy supersymmetry. And we don't. In fact, they're hoping to find some evidence of it at very high energies at the new Large Hadron Collider in Europe that just got completed not too long ago. So we don't observe low-energy supersymmetry, and the landscape seems to predict that. So there's reason to have some skepticism there. And then you can ask, well, are there enough universes in the landscape to give us the right properties? And we don't know for sure. I mean, it seems likely you need versions of string theory that are compatible with a positive cosmological constant, and it looks like there are at least 10 to the 500 such models, which could potentially cover the fine-tuning if they all existed, and we had any reason to believe that they all existed, and we don't, really. But there are some other, well, first of all, so let's take stock of where we are. And I suggest, you know how in Alice in Wonderland they talked about believing 6 impossible things before breakfast. I suggest we have 6 credulous conjectures before breakfast here. There is such a thing as an inflaton field, which we don't know that for sure. It's a postulate. It was invented to solve a specific problem. It bears no intrinsic relation to any of the other fields that exist in physics. Secondly, there's a potentially infinite number of bubble universes. Thirdly, there are strings. Strings exist. Fourthly, our universe has 6 additional hidden spatial dimensions. 7 if you embrace M theory. Fifth, there's an infinite number of compactifications of these additional dimensions if you allow for a negative cosmological constant. And each of them potentially corresponds via inflation to an infinity of actual universes. And when you put all of that together, finally, you've got a situation that explains away the fine-tuning of initial conditions. Laws of constant. Okay? Believe that? I've got some land in Florida I'd like to sell you. Okay, but what happens if you believe that? Well, it has some absurd consequences because you get a stupendously large space, much bigger than our universe, in fact, almost infinitely larger. What happens in such a context? Well, you get situations, physical situations, recurring. So somewhere out there in the multiverse, there's a clone of all of us, and we're sitting in a similar lecture theater, and I'm giving this talk. There's also another one where you're all sitting there, and I'm standing on my head in the corner. It just, you know, you name it, let your imagination run wild, and somewhere in the multiverse, that's exactly what's happening. Parallel realities. You know, Mother Teresa is an axe murderer. There's also another problem that physicists are rather worried about. It's called the Boltzmann. That physicists are rather worried about. It's called the Boltzmann brain problem. There was an article actually discussing how cosmologists were arguing back and forth about this. It appeared, I think, January 15th, 2008, in the New York Times by Dennis Overby. It was called Big Brain Theory. Have cosmologists lost theirs? Because essentially the problem is this. If you're looking at things from a quantum theoretic standpoint, it's much more probable that you get a fluctuation into a smaller volume than into a larger volume that had some regularity associated with it, like our universe does, with a 13.7 billion year history and all of us having personal histories and so on and so forth. When you get a really large space, it's more statistically likely, from a quantum mechanical perspective, that what fluctuates into existence is a single brain with the sensations being fed into it. Okay? And the problem here is that in the most common models of the multiverse, that is actually more likely than the fact that you and I exist the way that we take ourselves to, having a personal history. So in other words, you could say that the multiverse is falsified because the sort of people that we take ourselves to be aren't typical observers within it. And cosmologists have been trying to find a way around this, but it involves a lot of gerrymandering of mathematics. Okay. So, and then as a logical point, it seems to provide an all too easy explanation of anything that's happened or may happen. And by so doing, it really winds up explaining nothing at all. So why persist in that strategy? Well, this is what Leonard Susskind, who's a landscape theorist at Stanford University, had to say about it. If for some unforeseen reason the landscape turns out to be inconsistent, maybe for mathematical reasons or because it disagrees with observation, then as things stand now, we'll be in a very awkward position. For without any explanation of nature's fine-tunings, we'll be very hard-pressed to answer the ID critics.
Intelligent design. Yeah.
Intelligent design, ID. And as Bernard Carr put it, to the hardline physicist, the multiverse may not be entirely respectable, but it's at least preferable to invoking a creator. Indeed, anthropically inclined physicists like Susskind and Weinberg are attracted to the multiverse precisely because it seems to dispense with God as the explanation of cosmic design. Well, why would that be so important? This is what Richard Lewontin had to say. He's an evolutionary biologist at Harvard. Our willingness to accept scientific claims that are against common sense is the key to understanding the real struggle between science and the supernatural. We take the side of science in spite of the patent absurdity of some of its constructs, in spite of the tolerance of the scientific community for unsubstantiated just-so stories, because we have a prior commitment, a commitment to materialism. Moreover, that materialism is absolute, for we cannot allow a divine foot in the door. I mean, anyone who believes in God could believe in anything. Little irony here. To appeal to an omnipotent deity is to allow at any moment that the regularities of nature may be ruptured and miracles may happen. Well, in the multiverse, anything can happen, and it can happen for no reason at all. In other words, the materialist is forced to believe in random miracles as an explanatory principle. In a theistic universe, however, nothing happens without a reason, and miracles are therefore intelligently directed deviations from divinely maintained regularities, and thus are also expressions of a rational purpose. So, as a conclusion, then, I would suggest that scientific materialism is epistemically self-defeating because when you push it to the extremes that you have to make it try to explain everything, you find that it renders scientific rationality itself impossible. Thank you.